So S of 4 appears to be 3. S of 0 also appears to be 3. So it's 0. Okay, our average velocity is 0. You can also see that if you connected it, if you made a secant line. So if I marked S of 4 and made a secant line across, I can see that would be 0. Like the slope of that line would be 0. It's because I'm negative half of the time and positive the other half, and it's mirror images of each other, so they cancel out. Okay, does that make sense? Why that's happening? Because below 2 my velocity is negative, and above 2 my velocity is positive. Okay, then C wants the instantaneous velocity. Oops. The instantaneous velocity when t equals 4. So I need to use the equation. So the equation is t squared minus 4t plus 3. So if that's the position, what would velocity be? The derivative of that. So what would that be? Yep? Minus 4? Perfect. So the velocity at 4, if I just plug it in, 2 times 4 minus 4, is 4 meters per second. Okay, so my instantaneous velocity at 4 is 4 meters per second. Now the next one wants to know the instantaneous acceleration. So what will acceleration be? If velocity is 2t minus 4, what's the equation for acceleration? Yeah, so we take the derivative of the velocity, which is 2. So this actually has a constant acceleration. So the acceleration at 4 is 2, because it's just always going to be 2. Our graph is constantly accelerating at a value of 2. Okay? And then the last question, E wants to know where does the particle change directions? And I can see it in the position graph because I have a graph, or I could look at the velocity. If I wanted to use the velocity to tell where it changed directions, like say I didn't have a graph, how would I use the velocity equation I got in part C to help me figure out where it changes directions? Look for the 0. So if I set 2t minus 4 equal to 0, if I set the velocity equal to 0, I get t equals 2. Okay, and what that tells me for sure is that it changes direction at 2. If I didn't know what direction it was going on either way, what I would do is I would look at 2t minus 4, and I would consider a number line. We're going to end up seeing a lot of these, but I just want to do one really quick with you, where you put the 0 in the middle. So I put 2 there, and what I do is I test points. So I pick a number less than 2, like 0 is less than 2, and I pick a number more than 2, like 3, and I test them in this equation, in 2t minus 4. So I try 2 times 0 minus 4. What would that be? Negative 4. And I don't put negative 4 here, I just put a negative. Okay? Then I test the number higher than 2, so I try 3. And I get a positive. What that means is my graph is going from decreasing to increasing. So I can say not only that it changes direction at 2, but it goes from moving towards the left to moving towards the right at 2. I can make that statement. And I know that at 2, there'd be a minimum, because I know it's going from decreasing to increasing. Okay, so I can say all this stuff about 2 just based on using that derivative. So using the derivative, testing values of the derivative, and just checking, is it going up at that point or is it going down at that point? Because the positive negative tells you what direction things are going. Okay, so it's just helpful to look at. We're going to do a little bit of practice at velocity and stuff today. Okay, so this is just a bunch of stuff. We'll talk about it a little bit. It's not super vital, to be honest with you. And there's like a very specific example here about genetics that I don't know that I completely understand. But it's talking about just being relatively sensitive. So we talk about sensitivity. Sensitivity is basically about steepness. It's like about how quickly something's changing. So if a small change in x produces a big change in the value of the function being y. So like if a small change in x makes a big change in y, we call it sensitive. Like it's a sensitive function. So for instance, not like sensitive like it cries, but just sensitive like it overreacts. Okay, so y equals, if you have something like y equals, ooh, that's really weird. What is on? Okay, so if you have something like y equals 3 to the power of x, even. If I look at incremental changes, so if I like have an x value of, I don't know, 3, or no, let's look at bigger ones, like 6, okay, and x equals 6.1, okay, the y value that goes with 6 would be 3 to the power of 6, which is 729. And the y value that goes with 6.1 would be 813, or 814. So we see that a 0.1 change in x made a difference of almost 100 in y. Okay, that would be a sensitive function, because we're seeing just that it is jumping hugely based on like a really small change. Then it like describes this Mendel thing. Okay, it says, the hybridization through the study of peas with smooth skins and wrinkled skins. Is anyone taking bio? This is like a bio thing. Yeah, this is a bio thing. I think it's at the end of the year, though, or the end of the course. Through observation, he inferred that the proportion of peas in the next generation would be y equals 2p, bracket 1 minus p plus p squared. And you look at those graphs, and you can see that it's quite sensitive, I guess, is the point. Okay, but I don't know. But it's just important to know that some graphs are sensitive, and the sensitivity refers to how steep your graph is, how quickly it's changing. Okay, so we're going to look at marginal cost and marginal revenue. There will probably be a question or two of this on your test. It's pretty easy, though. So if you have a cost of production, that means the total cost for however many X are produced. So if you're like making shirts, okay, if it's like going to be the cost to make 500 shirts, okay, that would be the formula. The marginal cost is the rate of change of cost with respect to the level of production, so it's dc over dx. So for instance, if I told you that the marginal cost, like in my imaginary situation, of making shirts was 10, actually not 10, let's say it's 0.03, so that's actually something that kind of makes sense in that situation. Okay, 0.03, that would be dollars per shirt. So what it means is we're saying that for every shirt you add, it's going to have an increase in cost per shirt by 3 cents. And actually, it would probably be negative. It would probably be like negative 0.3. Because usually if you're making more of something, it becomes less expensive to make them, right? Like if you were making thousands of shirts, it would cost you less per shirt than if you were just trying to make 20 shirts. Does that make sense? Okay, because all the equipment and stuff. Like you have to consider that cost. Well, you're just using the exact same equipment if you buy like 1 million of it. So the marginal cost is the change of cost per item. Okay, that's what the marginal cost is. Now the marginal revenue is how much you make. Now revenue is not how much you make in total. Like it's not profit, right? Revenue is how much you would get paid for your shirts. You'd still have to subtract the cost. Does that make sense to everybody? Okay, so marginal revenue is the same thing. If I said that the marginal revenue, and this would make sense, would be something like, I don't know, 0.10 per shirt. What that means is for every additional shirt you make, you're going to make an additional 10 cents on each shirt. Okay, so it's how much you're making. Okay, so that's marginal revenue. So it's not, I don't know, it's not that confusing. I hope it's not that confusing. But when you see something like dr over dx, just remember that your units. So dr over dx, r is revenue, so that's dollars, and x is items. So it's dollars per item. Okay, that's how you can think about it if you get really stuck trying to figure out your units or whatever. So let's think about it. Okay. So suppose it costs x cubed minus 6x squared plus 15x dollars to produce x radiators when 8 to 10 radiators are produced. Okay, so it's telling us that's the cost. If you're only producing 8 to 10 radiators, it's going to cost you this much money. And that r of x equals x cubed minus 3x squared plus 12x gives the dollar revenue for selling x radiators. The shop produces 10 radiators a day. Find the marginal cost and the marginal revenue. And they will be this easy if you're given these problems. So, like, obviously, it's going to be a derivatives test. So, you should assume you need to find the derivative. But the word marginal tells you it's a derivative. But if you're on a test and you're asked for this and you don't remember what it is, use your brain and figure, I'm probably going to have to find the derivative. Okay? That's what you're going to have to do on every single question. So marginal cost is just C prime. So C prime here is 3x squared minus 12x plus 15. So C prime of what value should I plug in for x? 10. Yeah, 10. So it's going to be 300 minus 120 plus 15. So C prime of 10 is 195. Okay, and units would be what? Dollars per radiator. Okay, so that means that for every additional radiator at that point, at that instant, each additional radiator is going to cost me an additional $195. Okay? After 10. So to make my 11th radiator, it'll cost me $195. Okay? So then, if I find the revenue, so R prime, and you would explain that, you would just say you don't have to explain it really, you just have to say the marginal cost is $195 per radiator. You don't need to explain what that really means. But you need to know the units. Okay, so the revenue here would be 3x squared minus 6x. And so R prime of 10 is 300 minus 60, so that's 240.
Isn't it minus 6 plus 12?
Oh. Is it? I thought it was 3x squared.
3x squared.
Oh, plus 12. Sorry. I didn't think it had an x on it. My bad. Okay, so it's plus 12. So I need to add 12 to this. So it's not 240. It's 252. It's not letting me erase it. That's cool. It's $252 per radiator. Okay, so they make $252 per radiator. The additional cost would only be $195 per radiator. So their profit, you could just subtract those, right? For each radiator there, they're going to be making a profit of $57. If they made way more radiators, if they were making 50 radiators, what would you expect to see happen to the cost and to the cost? The cost would go down. Revenue would stay the same, actually, but the profit would go up because our cost is going down, right? So this is just some basic, everyone knows this. I think it's pretty straightforward that if you were making something, making something in bulk lets you make more money. Okay, so don't overthink it. Hey, just a review of the trig. The derivative of sine is cosine. The derivative of cosine is negative sine. Let's do the second one, because when we looked at it before, we didn't know quotient law. Okay, so if I'm trying to find the derivative of this, cosine x over 1 minus sine x, what would I do first? Quotient rule. So it's f prime g, and if you are having trouble remembering it, please write it down. F prime g minus g prime f over g squared. So write it down somewhere so that you can look at it as you do it, because you want to make sure you're doing it correctly, right?
Are we going to be given these
No.
formulas on the test? No. Why not?
Guys, you should just know them. It's not a formula, it's a method, so you should know the method.
What methods should you know, Callie?
Definitely product and quotient law.
Okay.
And you should know all the trig ones. Sine, cosine, and tan for sure. We're going to be using them. Okay? So the derivative of cosine is what?
Sine.
No,
Negative sine.
it's negative sine. So f prime is negative sine. You told me the other day you didn't know how to do quotient law, Ryan, so you should pay attention. Because it's right now I'm doing it. Okay? You were 2 here. Okay? G is what's on the bottom. So we have 1 minus sine x. Hey, Alex. Okay, minus g prime. What would be the derivative of 1 minus sine x?
Negative cosine.
It is negative cosine. So it'd be negative cosine times cosine all over 1 minus sine x squared. Okay, now on the bottom you never expand it, ever. Okay, the top you should usually expand. So we'll expand this out. One of the things I would do first is where I see negative, negative, I would just make those both positive. Okay, because two negatives make a positive. And I would multiply this out. So when I multiply that out, I do end up with sine squared x minus sine x plus cos squared x all over 1 minus sine x squared. Now, on top, I do actually have something that's simplifiable. Does anyone see it? That's 1. Sine squared plus cosine squared is 1. Okay, that's one that you have to know. Like, it's a very basic identity that sine squared plus cosine squared is equal to 1. So if you have sine squared plus cosine squared, you should simplify it to 1. So I have sine squared plus cosine squared. I can make that 1 minus sine x over 1 minus sine x squared, which then further simplifies. I can cancel off one of the 1 minus sine x's, so I end up with 1 over 1 minus sine x. Okay, so that one simplifies. Trig doesn't often simplify. A lot of the time it'll just stay what it was. But this is a situation where it did work out quite nicely. Obviously it was created that way to do that. Ryan, did you write it all down?
When creating these problems, can they just like start with the answer and work their
I don't know how they do it.
How do they figure out what equals simplify nicely?
I think if you started with the top, or like, yeah, if you started with the top and you thought about what the derivative of that's going to end up being, then you can kind of make the bottom match sort of thing. It would be hard to do though, to be honest. I'm not completely sure how they do them. This one worked out very well, so obviously it was planned, but okay. So these ones you should know, you should definitely know up to tan. Secant does kind of show up. They're really in order of importance, I would say, but sine, cosine, tangent you need to know. Let's do this with a second derivative of secant x. So if I was doing that, y equals secant x, so y prime would just be the derivative of secant x, which is what? It's on the left. It says right here, secant x times tan x. So then if I'm doing the derivative of that, so if I'm taking the second derivative of this, what will I have to do? Product rule, yeah. So I would have to make this f and this g. And so it's going to get quite ugly. The f prime would be secant x tan x times tan x plus the derivative of tan x, which is secant squared x times secant x. Now this actually works out not too badly because we can see it just ends up being secant x tan squared x plus secant cubed x, which you could remove a secant if you wanted to. I wouldn't though, I would probably just leave it like that. But you could factor out a secant if you wanted to. Okay, so it doesn't look that bad in the end, but you do have to do product rule, which makes it a little bit more complicated. Okay, so anytime you have a multiplication, you need to do product rule. For some reason, around this time, usually people start forgetting about the product rule, and they'll just start taking the derivative of both of the things and like multiplying them together. That doesn't work. Okay, so anytime there's a multiplication, you have to do product rule. Okay, let's have